Right, good morning, everybody, and thank you for joining me for today's Tech Talks. My name's Claire Cox, and I work for the technology consultancy Scott Logic. And I'm delighted to be joined by two of my colleagues this morning, Molly Pace and James Leftley. If you have a question for either of the speakers, they're very brief Tech Talks today. We're looking at about 15 minutes apiece. So if you'd like to ask a question, we will take them after each presentation. So get your questions into the question box and we'll take as many as we can. So let me introduce you to your first speaker today. Molly Pace studied neuroscience at St Andrews before joining Scott Logic as a developer. She's currently on secondment to the business development team, and we're very pleased to have her too. So without further ado, let me introduce you to Molly.
Thanks, Claire. As Claire said, I'm Molly. I've worked at Scott Logic since 2019, but prior to that, I studied neuroscience and computational neuroscience. And it was seeing the possibilities that tech opened up for the world of neuroscience that really sparked my interest in technology and development. And today I hope that I can share with you a few bits of insight into the influences that neuroscience has had on artificial intelligence. There is just a small caveat with this presentation in that I did it at a live tech and mix cocktail night at Scott Logic. So there are a few cocktail references. I am not condoning that you have one in hand at 10:30 in the morning. So first of all, I want to set some definitions of what I'm going to talk about today, because artificial intelligence is such a vast topic, and I want to make sure I set out what I mean when I'm referring to artificial intelligence today. First of all, I'd like to define intelligence, and a definition and tests for this have been disputed for a few years because they often have an element of a human bias. So I like to use the following definition when I'm talking about intelligence. And that is that intelligence is the ability of an agent, be that an animal, a robot, or a human, to perceive an environment and choose actions that increase its chances of achieving a goal. Artificial intelligence here is simply this intelligence demonstrated by machines. And when I'm talking about natural intelligence today, that's just intelligence which living organisms are born with and continue to acquire throughout their lifetime. The human brain is currently the best known demonstration of intelligence, artificial or natural. And when the concept of artificial intelligence was first introduced, nearly all the pioneers in the field were involved in both disciplines. For example, Turing in computing machinery and intelligence, and Marvin Minsky. And all the other founders in the AI field were also studying neuroscience at the time. More recently, as artificial intelligence has evolved, developers and researchers don't tend to pay as much attention to neuroscience as in the initial stages. Now, bear with me here for a cocktail-themed metaphor, but if an alien came down to Earth today, the first thing I would do is make them a margarita, because I think you want to show that alien the best thing Earth has to offer. And in my opinion, that's a margarita. Upon trying this margarita, an alien's mind would be blown. The first thing they want to do when they get back to their planet is make all their alien friends a margarita. And then they realize they've forgot to ask what's in a margarita. What is a glass? What is a lime? How does one shake? And to me, this is like exactly the same as us looking to artificial intelligence with not actually understanding the brain in the first place. Just in case you do want to know how to make the best margarita, I've also left a recipe on the bottom there. There are a few key ways in which I think neuroscience has influenced and should continue to influence artificial intelligence. The first is the emulation of natural intelligence. The original mission of pioneers in artificial intelligence was to really emulate natural intelligence. There was an aspiration to build an intelligent system which could adapt and grow and show human level intelligence. If we really want to emulate natural intelligence, we need to continue to be influenced by an understanding of that natural intelligence system, the brain. The second is that as we uncover more about the structure of the brain, we can take and apply and make inferences on the ways that we can make both the hardware and software of AI replicate this natural structure of the brain and in turn be more effective as a system. Thirdly, when we create models and algorithms in AI and complete the training of artificial intelligence systems, it can be hard to know how successful these models are. Neuroscience can provide a means to validate and verify the accuracy of models that we build in artificial systems. Today, I'm mainly going to talk around the second point about the structure and the inner workings of the brain and how we can apply that to artificial intelligence to be more effective. First, I'm going to nerd out a bit about the brain. So brains are amazing. They have an insane calculation capacity. We have 86 billion neurons in the brain, each connected to thousands of other neurons through synapses. And every synapse can compute 200 operations per second. Some maths on that means the brain could compute around 20 billion operations per second. And this mind-blowing calculation capacity runs off about 400 calories today, give or take 2 Snickers is about what we're running off. That's 25 watts, less than the power of the average light bulb. And I don't know about your light bulbs, but mine certainly aren't processing 20 billion operations per second. This low energy consumption of the brain is often attributed to the brain's noise tolerance, flexibility, and its parallelization of calculations. And these are things that we should take forward and apply to artificial intelligence. The main example of parallel processing in the brain comes from visual processing. We are able to process information on color, motion, shape, and depth of our environment and objects in it simultaneously. These pieces of information are individually analyzed and then compared to stored memories to identify what we are seeing. A little example of how this works is something called the Stroop effect. So if I show you these set of words, you will process both the color and the written word in a parallelized manner. If I ask you to read me the ink colors here, that should be easy to do. If I also ask you to read me the written word, that should be easy to do, because in this example, they are congruent with each other. However, if I put up this example where the ink color and the word demonstrate different things and are incongruent, and ask you to either identify the color of the ink or read me the written word, it's going to be harder to do. In this case, the stronger neural pathway in humans takes over because they have a higher speed of connection and you can respond initially faster. So most people find when they do this, if I asked you to read out either the words or the ink color in the second row, most people would find that it's easier to read the words. And that's because as humans, we are communicators. Language is a big part of who we are and how we get around our daily life. So those neural pathways are stronger and most people find that easier. This is just an example of how parallel processing works in the brain and how it's a key aspect to the speed and adaptability of processing systems in natural intelligence. It's something that's essential in artificial intelligence. If we want to achieve the same levels of efficiency, we need to be focusing on parallel processing. The next aspect of the brain that I think we need to bring it into artificial intelligence is how extremely plastic it is, not only in the strength and existence of connections, but we can actually make physical changes in our brain depending on our training or our day-to-day life. Now, I've made a fool of myself before because most of my friends in my neuroscience circle recognize these brains straight away, but I'm assuming people here don't. So these brains are of black cab drivers in London. I'm sure some of you may have heard that black cab drivers have to sit an exam where they can relay how they would get from one part of London to another part of London and how they would do so quickly and alternative routes if there's road closures. This means they've got an incredible spatial memory, so enhanced and really efficient systems. And people have looked at the brains and the physicality of these black cab drivers. The part of the brain that's responsible for this spatial memory is called the hippocampus. And these images here are MRI scans that highlight the difference in size of the hippocampus in black cab drivers compared to the general population. They have not just enhanced the connections, their brain has physically changed in response to what they're doing in their day-to-day life. It's a bit of a wild card, but I think maybe we should be thinking not just about having adaptable artificial systems, but also adaptable hardware in this way. We need to have scalable memory systems that can change not just in how they connect, but how they are physically in the world. The last thing I'm going to talk about today, in which I think we should be looking to neuroscience to influence artificial intelligence, is the spiking behavior of neurons. So this is how they communicate from one neuron to another, is by something called an action potential. It's basically an electronic wave that once a neuron reaches a certain threshold, it will either spike and pass on that information, or it will not spike. When reading into biological influences of artificial intelligence, there are many accounts referring to neuron firing of action potentials as binary coding. And so we've gone that way of either it does or it doesn't. But in actuality, the brain takes more information from action potentials rather than just whether it happens or not. Processing of information by the brain is not simply taken from whether they spike, but also encoded by other factors such as spike timing, firing rate, and the time between potential spikes, called the interspike interval. The intricacy of timing between spikes in neuroscience determines whether a pathway is enhanced, weakened, or completely lost. There's a slight oversimplification in my mind if we are coding our artificial systems in whether they do or they don't to emulate these neuron firings. AI needs to utilize methods that can make inferences from delays and dynamics between analog signals rather than binary signals. In this presentation, I've only discussed what AI can take from neuroscience, and I think should continue to take from neuroscience. But obviously, this is a two-way relationship. Artificial intelligence allows us to create human-like simulation of the brain for research purposes, and any study of the brain that doesn't come from at the cost of living organisms or animals, to me, is a win. However, I think it's important that as we move forward in artificial intelligence, that we do not forget to look back, appreciate, and understand the root of the field, which is the brain. As both fields advance, they can only provide more insight into the other. And as industries, I think we need to focus on keeping that communication between artificial intelligence and neuroscience open and strong. I hope I've been able to teach you a little bit about my passion of the brain and how that has influenced artificial intelligence today. I think we've got a few minutes for questions, so I'll pass over to Claire if you can read some from the chat.
That is great, Molly. Thank you so much for that. That was absolutely fascinating. We have got a couple of questions in already. I'm going to start you off with one that says, do you think there's an issue with what we refer to as intelligence in the computer science field?
Yeah, I think sometimes, in my opinion, we're maybe a bit too quick to call something intelligent, and rather than just a system that is acting as so highly trained, and maybe our intelligence, we need to focus on whether something is really choosing to interact with its environment to come to that goal that I talked about at the beginning. Yeah, I think sometimes we need to maybe put some stricter limits on what we actually refer to as intelligence when we're talking about these systems.
Great. Now I've got a long one to read out for you now. You ready for this one? So, any suggestions on how the neuroscience ideas are translated to computer/hardware realization? FPGAs seem to cover parallelization, have I said that correctly? And hardware plasticity, but not the signal levels. Would you suggest something like analog processing to be a way forward?
Yeah, I think is the short answer. When I was talking there about how action potentials interact and create those strengths in the brain, it is definitely something that we need to focus on analog processing in order to get all the information that we can from those pathways. So yes, in the short answer.
Great stuff. Right, I've got one more for you.
Yep.
This one says, how does the way in which we train neural networks /AI compare to learning in natural intelligence?
Yeah, this is really interesting. So often we'll train neural networks, say, to recognize objects using labeled pieces of information. And while this is great for training them, it's definitely different from learning in the real world. There's examples of that when you see like somebody with a young child pointing at their parent and going, "This is mom, say mom." But that doesn't happen with everything that we learn. And we process when we're young billions of pieces of unlabeled information. And we're also born inherently with information that seems to be in our genetics. So this training is not exactly similar to how real brains learn. Yeah.
That's brilliant. Well, thank you so much, Molly.
No worries.
If anyone does have any more questions for Molly, if you think of them, we will have more Q&A time at the end. But I'm going to switch over to and introduce you to your next speaker now, and that's James Leftley. James is a lead developer at Scott Logic. He's worked across a range of domains, including energy trading, finance, and the public sector. Most recently, James has worked on a large microservices solution with strict high availability and security requirements, a Kubernetes platform and a Kafka platform, all built in the cloud. And James is going to talk to us about resilient systems and experimentation. So over to you, James.
Well, thank you very much, Claire. Good morning, everyone. So today I'll be talking about the resilient systems and how experimentation can help us improve resiliency. So in October last year, you might have switched on the news or gone to your news website, or possibly even gone to Facebook, Instagram, or WhatsApp and noticed that something had gone wrong. In October last year, Facebook made some BGP, Border Gateway Protocol changes, which led to users being unable to resolve Facebook's domain names, which caused disruption for around 6 hours to Facebook, Instagram, and WhatsApp. Facebook has got a user base of around 3.5 billion users, And this had significant impacts. Some companies rely on Facebook for marketing and for communication with customers. The share price of Facebook itself dropped by 4.9% on that day. According to Bloomberg, Facebook CEO's Mark Zuckerberg's personal wealth fell by more than $6 billion US. According to some reports, Facebook lost at least $60 million in advertising revenue. Internally at Facebook, employees had issues accessing their emails. Also reported in the New York Times was that some employees couldn't even get into the office. Their smart cards weren't working. And the financial loss from an outage can be very varied based on the size of an organization, of a company, and the industry they work in. A Gartner article from 2014 stated that the number they typically cite is around $5,600 US per minute, and that extrapolates to well over $300,000 per hour. There are impacts in the developing world as well. Facebook have a free basics program, and that affected communication, businesses, and humanitarian work. And it's probably not just Facebook that you will have seen in the news when something goes wrong. Facebook, again, in March 2019, had a server configuration change that caused disruption for around 14 hours. This didn't just affect Facebook, it also affected other services such as Spotify and Tinder that uses Facebook's login to access the services. In November 2020, AWS had an outage. They had a technical problem with some of their data centers in North Virginia. Thousands of customers use AWS, and their services were disrupted for several hours. I know my Ring smart doorbell at home stopped working. Some people on Twitter reporting their robot vacuum cleaners weren't working due to the outage in US East 1, which is AWS's North Virginia region, their collection of data centers there. December 2020, Google had an internal storage quota issue which caused issues with authentication. This lasted around an hour and a half and affected Gmail, YouTube, and Google Drive. June of last year, Fastly, an edge computing provider, had a bug in their software which was previously unknown to them, and it was accidentally triggered by a customer. The issue was detected within a minute and fixed within an hour, but it caused disruption for the UK government website, Amazon, Reddit, Twitch, GitHub, Shopify, Spotify, news sites, lots of customers. An Akamai content delivery network provider experienced a bug within the domain name system, DNS. This lasted around an hour and affected lots of services, including Airbnb, Expedia, and Salesforce. I just want to take a moment to note, I really don't mean to be at all critical of any of these companies or any of the people running them. Things do go wrong, and the companies I just listed are really towards the best end of being able to recover from when issues happen. But I want to sort of say that things do happen. It does affect people's lives. But really, yes, I have a lot of empathy for the people operating and running these systems. And really, everything fails all the time. This is a quote by Werner Vogels, VP and CTO of Amazon. And I think it's certainly worthwhile when developing systems to put effort into preventing failures from happening in the first place. This is a really important foundation of reliability. However, I also think it's inevitable that some failures will happen. So we shouldn't put all of our efforts into just preventing failures, but also accepting that failures will happen and putting effort into knowing when failures happen, that we can build confidence, that we can recover in a quick and safe manner. So return to the availability of the system and minimize data loss. And sort of things that fail that can happen can be a certificate expires, perhaps a domain isn't renewed when it should be. It could be a cable's been unplugged by accident in a data center. It could be a piece of hardware like a hard drive has failed. It could be an incorrect cache value. There might be a power outage at a data center or a fire. There could be a bug introduced in a new software release, or there could be a deployment process which fails. So I said I'm going to be talking about resilience. Reliability first, for me, is sort of an umbrella term, and it includes lots of different factors, one of which is resilience. So you can define reliability as the ability of a system to perform its intended function correctly and consistently when it is expected to. And operations contributes to reliability, being able to operate the system, being able to deploy, make fixes, make changes, and operate the system in a safe way. The security can affect reliability. If a system has vulnerabilities that can be exploited, that can affect the ability of the system to perform its function. Performance. If a system can't handle the sort of load it might expect, that can affect availability and affect the response times, or a system could become unavailable altogether. There's the cost. Reliability will tend to cost more the more reliable the system is. There might be more underlying hardware, more time and effort to build the reliability, and that has to be balanced with what the business needs are and how much the kind of cost the cost is and the value of making a system more reliable. And then finally, the resilience. So I'd say the resilience is the ability of a system to recover from failures and continue to function. Last year, the Accelerate State of DevOps report was published by the DevOps Research and Assessment team at Google Cloud. And the report examines the practices that drive successful software delivery and operational performance. There are 4 metrics around successful software delivery in the report. This includes deployment frequency, lead time for changes, time to restore service, and change failure rates. And the team there have gathered data over the past several years and conducted research, and they've developed and validated these 4 metrics. And for each of these metrics, there's an indication of the elite performers, high, medium, and low performers. And I wanted to focus on the time to restore service because this is very much the resilience area. So if you look at time to restore service as a metric of software delivery, elite performers can typically restore service from an unplanned outage in less than an hour. Low performers take more than 6 months. So elite performers are 6,570 times faster to recover from incidents on average. So if you're looking at software delivery metrics in this report, then being resilient can certainly mean that you're kind of, as a measure of software delivery, it's certainly a good thing to look into. So experimentation. Experimentation is one area that I think's really exciting, really interesting, and an area that we still have a lot to learn in software. There are lots of other really important factors for resiliency. So knowing what the requirements of the system are, knowing how to gather that information and define them, knowing what metrics to measure the resiliency of a system on and assess whether you're meeting the requirements, the underlying architecture patterns and approaches for the application, infrastructure, processes and people, and testing. And I really think you need those things first before looking into experimentation. But I do think experimentation is a really interesting area and something definitely worth considering if you're concerned about resiliency. So why experiment? A lot of systems that I've been working on recently are fairly large scale distributed systems, maybe composed of many different services. And these advances have been great. I think they can often increase the velocity of development. However, they can be complex. And even if individual components within the distributed system are working, interactions between these components can lead to unpredictable outcomes. And when you compound these with real world events that can cause disruption, like I mentioned before, whether it could be a security vulnerability or a hardware failure or a data center outage. This can lead to hard to predict disruptions. So we can experiment with these systems to try and surface the weaknesses in the systems before they become critical issues that are affecting the end users. And the sort of things that we might find are improper configuration. That might mean that a service doesn't fall back correctly if it fails. There could be issues with timeouts between services that could lead to cascading failures. Or there could be an outage when too much traffic is received to one particular component. Around 2010, Netflix were documenting their migration from their own on-premise data centers to AWS. And as part of that migration, they published on their technology blog about a tool that they used called Chaos Monkey. And the Chaos Monkey was a piece of software that runs and it randomly kills the instances that Netflix runs on. And this might seem kind of a bit crazy at first, deliberately terminating kind of your production instances. But the idea was that if they set the expectation for the teams developing the systems that in production, these instances will be terminated, then people are going to build and design their systems to work in that case. So, it might be that this happens unintentionally once a year, but if it's happening all of the time, you're building confidence that if an unexpected outage does happen, the system will be resilient. So Chaos Monkey is a tool, and I think that chaos engineering is a phrase that often comes up when people are talking about building resilient systems, and Chaos Monkey at Netflix really was, I believe, what popularized chaos engineering. Here we're talking about running Chaos Monkey in a production environment. In reality, there may be toggles that don't apply Chaos Monkey to certain services. And I think since 2010, sort of the field of chaos engineering has matured. So chaos engineering is the discipline of experimenting on the system in order to build confidence in the system's capability to withstand turbulent conditions in production. So chaos engineering can take many forms, but a chaos engineering experiment may typically look something like this. So I mentioned before, kind of Chaos Monkey is run in production at Netflix, but you could run chaos engineering experiments in non-production environments. You can run them one-off periodically, for example, as part of a game day, which I'll talk about next. Or they could be even automated as part of a CI/CD pipeline. So typically the first thing you'll do is you'll define the normal behavior or the steady state of a system. This is the sort of measurable output that indicates normal behavior. So for example, certain response times, percentage of sort of successful responses and requests. Create a hypothesis, something that you want to test as part of the experiment. Inject some failures into the system. This could be increasing latency of responses. It could be terminating virtual machines. It might be simulating a failure to a third-party service that you rely on. You can then stop the experiment. This might stop early based on metrics and alarms in place, particularly if you're doing something in a production environment. And then you can stop, review the experiment, see what happens, and learn. So for an example, you might create a hypothesis where if you have a system running in two data centers, one data center is in London, the other is in Edinburgh, you might have designed your system so that the system will continue to run and users won't notice if one of the data centers becomes unavailable. So your hypothesis could be that the system remains available and the response times remain within a given metric. You could then simulate the failure of one of the data centers becoming unavailable, observe what happens, and stop and review. So game days. Game days is another way you can experiment. I've read back as in the sort of early 2000s, Amazon were running game days, and these are one way to test the operational resiliency by simulating lifelike failures to systems. And this is a really good way to sort of test the socio-technical factors of a system. So not just the software and the infrastructure, but also the people who run the software and the infrastructure and how they interact. So these can, for example, be carried out on replicas of production or in production itself. And a game day will simulate a failure or an event, and then you'll see how the team and the processes respond. So typically, the first thing you'll do is identify the services and people that you want to test as part of the game day process. This could be disaster recovery, it could be resilience, maybe there's an outage in a data center. You identify the services that this might affect and the people responsible. When you're defining you define the scenario you want to run. Usually you'll have a small group of people who will define the scenario, will know what's happening, and will publicize ahead of time that a game day will be taking place, but will not tell the people who are operating the system the specifics of what event will be simulated. So you have a small group of people who are responsible for defining it, introducing the failure, and then another group of people who will be responsible for responding to what happens. And you can observe what happens. Does everything go to plan? Does something go wrong? And then you can analyze and see if there's anything differently that you could do to improve in the future. So a good place to start for a game day is maybe if there's been an outage to a system previously, is simulating that again and seeing how the team and the system reacts. So to wrap up, failures are inevitable. Embrace these failures, learn how to adapt, and consider experimentation. I've just mentioned a couple of ways that you can maybe look into doing that, and these can help us generate new information and build confidence in the technology, processes, and people that operate our systems. So thank you very much for listening. I know there's the opportunity for questions now, but please feel free to reach out to me by email at a later date as well. Thank you.
Great stuff. Thank you, James. I've got a question here for you that says, when running a game day, would giving people notice that an event is upcoming give them time to prepare?
Yeah, so I think there's a balance here. I think game days, depending on what you're simulating and where, it's good for people to know that one's upcoming because it will take time away from other work. So for giving some people notice and making sure people are aware it's happening is important. I also think, as I mentioned, you probably don't want to say game day's coming and then lots of people to take lots of holiday, so no one's around, for example, because they want to avoid it. So maybe a week or two's notice that a game day's happening is reasonable. And given that you typically won't tell them what specific event has been simulated, it's not really possible to prepare too much. Another approach can be, you can say what is happening and when, and use that as a way to encourage people to prepare for that particular event. You might want them to make specific changes before, in which case you could tell them. So I don't think there's one sort of right answer. There's trade-offs to different approaches.
That's great advice. Right, I've got one more question for you here, and that's, how would you differentiate chaos engineering from integration testing?
So I think chaos engineering will typically be done at a large scale. It will typically be done on the system as a whole. I think it will typically involve people and the processes as well as the software itself and how people interact with the systems. And I think the chaos engineering is often focused on running experiments where you might not know exactly what the outcome will be. It's more to uncover new information rather than perhaps kind of test specific cases with easier to measure known outcomes.
That's great. Thank you so much. Well, all that leaves me time to say is thank you so much to James and Molly for today's fascinating talks. And thank you so much for joining us as well. If you've enjoyed today's Tech Talks, do check out the Scott Logic YouTube channel for more of our videos. And also you can check out our technology blog at scottlogic.com. So until next time, bye for now.